Morning everybody. I introduce myself. My name is T. Henson. I am working as assistant professor in the Department of Mathematics, St.Joseph's College of Arts and Science, Cuddalore. So good morning everybody. I am going to teach the subject ordinary differential equation. Unit 5. The topic is existence and the uniqueness of function. Now we are going to see the definition for Lipchitz condition. So a function f of t, x defined in a region t subset of R square is said to satisfy Lipchitz condition in the variables x with the Lipchitz constant k if the inequality f of t, x1 minus f of t, x2 less than or equal to k into modulus x1 minus x2 wholes. T, x1 and t, x2 are the points in D. In such case, we define F to be a member of the class Lipchitz. With the D is a domain with the Lipchitz constant k. As a sequence of the definition, function f of t, x satisfies Lipchitz condition equal to only if there exists a constant k greater than 0 such that this inequality is to satisfy, that is modulus f of t, x1 minus f of t, x2 divided by modulus x1 minus x2 less than or equal to k. Here x1 not equal to x2. So whenever these 2 points are in D. Now we are going to see a theorem. First it is a statement of the theorem. Let f of t, x be a continuous function defined over a rectangular region R equal to the set of all t, x such that modulus t minus t naught less than or equal to p, modulus x minus x naught less than or equal to q. Here p and q are some positive real numbers. Let dou f by dou f, dou f by dou x be defined and continuous on R. Then prove that the function f of t, x satisfies the Lipchitz condition in R. Now we are going to write the proof. Since dou f by dou x is defined and continuous in R, there exists a positive constant a such that this condition is to satisfy. That is modulus of dou f by dou x of t, x is less than or equal to a. This can be taken as equal to 1. We need 2 points in R. Then by mean value theorem, in differential calculus, there exists a number which lies between x1 and x2 such that f of t, x1 minus f of t, x2 equal to dou f by dou x of t, x into x1 minus x2. Since the point t, x lies in R, then we calculate this by taking modulus value for this. So we take the modulus value, then this can be written like this. That is modulus f of t, x1 minus f of t, x2 is equal to modulus dou f by dou x of t, x into x1 minus x2. Now you can split this modulus value, modulus expression like this. That is modulus dou f by dou x of t, x into modulus x1 minus x2. So this is replaced by a because so here we are using this equation 1. So we are using this equation 1 and this is replaced by capital A. Then into modulus x1 minus x2. So thus it satisfies the Lipchitz condition. Here the Lipchitz constant is A. So this complete the next problem. Show that the function f of t, x is equal to x plus x square into cos t by t square satisfies Lipchitz condition in modulus x less than 1 and modulus t minus 1 less than 1 by 2 and find the Lipschitz constant. Now we are going to write the solution for this problem. Now we calculate this expression f of t comma x1 minus f of t comma x2 is equal to x1 plus x1 square into cos t by t square minus x2 plus x2 square into cos t by t square. Now we can simplify this by taking out the common element cos t by t square into x1 plus x1 square minus x2 plus x2 square. Now we can simplify this. So this can be written as cos t by t square into x1 minus x2 plus x1 minus x2 into x1 plus x2. So in this expression we can take out the common element x1 minus x2. Then the remaining element will be 1 plus x1 plus x2. So we have simplified this expression for convenient form. Next we can find the modulus. So modulus of f of t comma x1 minus f of t comma x2 is equal to modulus cos t by t square into x1 minus x2 into 1 plus x1 plus x2. This can be written as modulus cos t by t square into modulus x1 minus x2 into modulus 1 plus x1 plus x2. So this modulus of f of t comma x1 minus f of t comma x2 is less than or equal to modulus cos t by t square into modulus x1 minus x2 into 1 plus x1 plus x2. This can be taken as equation number 1. Now we use the condition since modulus x is less than 1 and modulus t minus 1 is less than 1 by 2. This can be written as minus 1 by 2 less than t minus 1 less than 1 by 2. So in this expression each and every element is to be added by 1. So this can be written as 1 minus 1 by 2 less than t less than 1 by 2 plus 1. Now we simplify this expression. So 1 minus 1 by 2, that is 1 by 2. Then t minus 1 plus 1, that is reduced to t. Then 1 by 2 plus 1, that is 3 by 2. So maximize the right hand side of equation 1. So the equation 1 is modulus f of t comma x1 minus f of t comma x2 less than or equal to modulus cos t by t square into modulus x1 minus x2 into 1 plus modulus 1 plus x1 plus x2. Here modulus x1 is less than 1, modulus x2 is less than 1. So the modulus 1 plus x1 plus x2 is less than 3. So that can be written here. So therefore modulus of f of t comma x1 minus f of t comma x2 less than or equal to 1 by 2 whole square into modulus x1 minus x2. Here modulus of 1 plus x1 plus x2 can be replaced by 3. So here 1 by 4, 1 by 1 by 4, this 4 goes to numerator, that is 4 into modulus x1 minus x2 into 3. Now we can multiply this, we get 4 into 3, 12. Therefore the modulus f of t comma x1 minus f of t comma x2 less than or equal to 12 into modulus x1 minus x2. Therefore the given function satisfies the Lipschitz condition and the Lipschitz constant is 12. So this completes the problem.